This video provides an overview of an analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight into the dynamics of a fire that resulted in 2 line-of-duty deaths. On June 2, 2011, a fire in a multi-level residential structure claimed the life of a lieutenant and firefighter paramedic from Engine 26 of the San Francisco Fire Department. NIST examined the fire dynamics of this incident at the request of NIOSH and the San Francisco Fire Department. At 10:45 in the morning, a call was dispatched for a reported fire due to an electrical short. Engine 26 arrived on scene within 3 minutes of the dispatch and reported light smoke conditions. They made entry through the front door with 1 3/4-inch hose line. At approximately 10:54, about 6 minutes after the arrival of Engine 26, Battalion Chief 9 followed the Engine 26 hose line up the front stairs, into the front door, and then down the stairs to the first floor or street level of the house. Battalion Chief 9 had a face-to-face discussion with the victims. During this discussion, Engine 26 confirms that the fire is below them, and Battalion Chief 9 indicates that the attack will be made from the basement level on the B side. The battalion chief exited the building. Engine 26 remained in position near the top of the stairway leading into the basement. This was the last communication with the Engine 26 crew members inside of the structure. Within 11 minutes of Engine 26's arrival on the scene, the large windows that made up most of the side sea wall of the basement level began to fail due to heat from the fire. As the windows broke, fresh air mixed with hot fuel-rich gases in the basement, which increased the heat release rate of the fire. The increase in heat release rate resulted in the rapid failure of the 6 window panels. It took less than 2 minutes for all of the windows to fail. After the rear basement windows began to self-vent, Engine 24 and Rescue 1A tried to make entry through the pedestrian door in the garage to attack the fire, but they were forced back by extreme heat and heavy black smoke. With the pedestrian door between the garage and the first-floor hallway open, heavy black smoke began flowing out of the open garage door at street level on Side A. Within a minute of this change, the Side B door on the basement level was forced open. Battalion Chief 9 reported heavy fire and smoke. Engine 11 tried to make entry into the basement, but they were forced back by the heat. Battalion Chief 9 requested a second hose line. Incident Command attempted to contact Engine 26 several times via radio, with no reply. By 11:02, both Engine 11 and Engine 32 had made entry through the Side B door into the basement and initiated suppression operations. At approximately 11:08, the lieutenant and firefighter paramedic from Engine 26 were found in the first-floor hallway between the top of the stairs from the basement level and the door to the garage. Both of the Engine 26 crew members died of their injuries sustained in the fire. NIST's Fire Dynamic Simulator, or FDS, was used to provide insight into the dynamics of this structure fire. The results of an FDS simulation are visualized with another NIST program called SmokeView. The inputs and details for the FDS simulations are documented in NIST Technical Note 1856. The fire started in the basement, near the balcony windows on the rear of the structure. The fire spread to a large sectional sofa in the center of the basement living room area. Based on an assessment of the fuel load in the burned area of the basement, the estimated peak heat release rate of the furnishings and interior finish was approximately 20 megawatts. However, the lack of oxygen limited the fire growth until the rear basement windows vented. As seen in the heat release rate graph, after the windows failed and allowed additional oxygen to mix with hot fuel gases in the basement, the fire rapidly increased from less than 5 megawatts to more than 25 megawatts in less than a minute after the first window self-vented. The comparison of photographs from the incident and images from SmokeView shows the rapid fire growth initiated by the uncontrolled ventilation of the rear basement windows. The photographs show the fire incident time, while the SmokeView images show the simulation time. The comparison of a photograph from the incident and from the simulation shows the condition on the front side of the house at street level, as the rear basement windows were self-venting. Now we will use output from the simulation to understand the flow path within the multi-level structure. Fire gases move from regions of higher pressure to regions of lower pressure. This video shows the pressure plane along the center of the stairway from the basement to the laundry room landing between the basement and the first floor. An estimate of the pressure increase is shown before and after the first basement window failed. This video shows the pressure plane along the center of the stairway from the basement to the laundry room landing between the basement and the first floor. An estimate of the pressure increase is shown before and after the first basement window failed. One of the hazards to firefighters located in the exhaust portion of the flow path is convective heat transfer from the fire gases. Convective heat transfer depends on the velocity, the amount of turbulence, and the temperature of the fire gases. This video shows a comparison of gas velocity estimates in the stairway before and after the basement windows self-vented. Another way to visualize velocity with smoke view is by using arrows or vectors. In this video, the vectors show both gas flow direction and gas flow speed. This is also representative of the amount of turbulence or mixing within the flow path. Notice the gas flow circulation pattern on the landing, which indicates a very turbulent or well-mixed flow. This video shows the calculated change in gas temperatures as a result of the fire's rapid increase in heat release rate before and after the windows self-vented. These images show the flow path from the fire on the basement level 2 minutes after the first basement window failed. At this time, all of the rear basement windows have failed. The hot gases in the basement are flowing up the stairwell, then splitting on the first floor, with some of the flow continuing up another stairwell to the open front door, and the rest of the hot gas flow moving out of the open pedestrian doorway through the garage. Notice that the open basement windows on the rear of the house serve as bidirectional vents, with fire gases exiting the upper portions and air entering the lower portions. While on the front side of the house, the front door and the door to the garage are unidirectional vents, serving only as an exhaust for the fire gases. There have been many previous fire incidents in which changes in the flow paths have had an adverse impact on firefighter and occupant safety. Fires with rapidly developing or changing flow paths are a significant hazard to firefighters. The development of a flow path could be caused by the failure of a component of the structure, such as a door, window, or portion of a ceiling, wall, or floor. Environmental conditions, such as wind, can generate hazardous thermal conditions within a flow path. Stay upwind of the fire or keep the wind at your back. Uncoordinated ventilation or uncontrolled doors can also be the cause of increased thermal hazards within a flow path. In this fire incident, the thermal degradation of vinyl-framed windows and sliding glass doors resulted in the self-venting of a wall of windows 19 feet wide on the rear basement wall. The window opening allowed hot gases to flow out of the windows and mix with oxygen, which enabled the fire to spread up the rear of the structure. Oxygen entrained into the structure enabled additional fire growth in the living room area of the basement. Failure of the rear windows resulted in a rapid increase in temperature, velocity, and mixing of the fire gases in the stairs and the first floor hallway. Conditions changed from tenable to untenable within seconds. Prediction of the failure mode and failure time of a building component is not a reasonable expectation given the large number of unknowns that firefighters face on the fire ground. Research has been conducted by NIST and UL with fire departments across the country on exterior fire attack. The studies have shown the importance of scene size-up prior to beginning interior fire operations in order to choose tactics that would not only be the most effective, but also increase the safety of the operations. The experiments in single-family homes have shown that once the basement fire was located during size-up, the most effective fire attack was made from the same level. When sizing up a structure fire, choose your tactics with potential flow paths in mind. Recall that in a flow path, the hot gases move from a region of higher pressure to a region of lower pressure. Firefighters located in the flow path downstream of the fire can be exposed to lethal levels of heat. Firefighters positioned in the flow path above the fire are in a high hazard and potentially deadly location. It is critical that tactics are chosen so firefighters are not caught in this position. For more information on this incident, see NIOSH Report 2012-28, San Francisco Fire Department Safety Investigation Report, Incident 11050532, and NIST Technical Note 1856. These reports and other information on flow paths and fire dynamics can be found on the NIST Firefighting Technology website. For updates, follow NIST on Twitter.